Hi class, I'm gonna talk about some of the assignment problems just to give out some hints here. So unless you really need a hints, so you can take a look at the video. Otherwise, I encourage you to do it first. Okay, when you have troubles, then can come and take a look at this video tutorials. Okay, so problem number 1, I already made a video tutorial, so you can take a look at that one. And so I'll start from problem 2 here. Problem 2 is not that difficult. I think for the first portion, calculate the volume of this one. It's pretty straightforward, and you just follow the procedures, right? Essentially, you need to draw a lines across the shadow, okay, and find the first contact and the second contact. Okay, make sure it's in Cartesian coordinates. Now, what I want to try to see is regarding the part B. Let's see, you're gonna do part B number 1. So basically, you're required to integrate in this order at here. Okay. Now, when you are required to integrate in this order, apparently this first integral is back to y. Then what we're gonna do is we're gonna look at the shadow of the solid, which is gonna be in x and z plane. Okay, so finding the y limit, and that's pretty straightforward. What you need to do is you draw a line. Okay, let's use the other line there. So you draw an arrow line, okay, across this whole solid. The first contact and the second contact will give you the lower and higher limit for the y. So apparently the y mean is x squared, and y max is 1 minus z. Okay. Now, in order to find the integral limit for x and z, we need to look at the shadow of this object. Now, what is the shadow of this object? Basically, the shadow here. Okay, the shadow here is the projection of the solid. Okay, the projection of the solid in x, z plane. Okay. So this might be one. You might be wondering, what kind of a shadow? What kind of shadow does it look like when you project into XZ plane? So basically, it's this surface, right? It's the right view, right? It's the right view. When you project this surface into the XZ plane, so what you're gonna look at here is you're gonna look at a sort of a parabola, right? A parabola here. So this is Z. This is X here. Then you're gonna look at something like this. Okay. Now the problem is, what is the function for this curve, right? What is function of this? And the function of the curve, basically, when you project that into there, it's a part of the it's part of this surface, right? Which is described by y equal to x squared. So this guy here is actually just x squared plus z equal to 1. Okay. So that's basically the curve surface here. Now, in order to find x and z limit, so you're trying to find a z limit first. Then what we're going to have to do, we're going to have to draw arrow lines, okay, across the shadow in the direction of z-axis. So the z limit, the mean is 0, and the max is 1 minus x squared. Okay, and now you need to sweep this line across the whole shadow. Okay. So across the whole shadow, then you find the vertices contain the whole shadow here. Then apparently the x mean and y mean x mean and x max, okay, is going to be just -1 to 1. Okay, so that's how you're gonna look for the part B. Okay, so similarly, you can do part B for 2, 3, 4. Okay, so get used to the procedures of finding the limits in Cartesian coordinates. Okay. So let's take a look at problem 3. Now this one, not much actually. So what you really need to do is you calculate the volume of this one in the first quadrant here, and multiply by 8. That'll give you the total volume intersected by the two cylinders. Okay. And remember, this one you were doing in Cartesian coordinates. Okay. Don't use polar, use Cartesian coordinate as required by the question here. Okay, so you're gonna draw a lines. You're gonna draw a line across the shadow. Okay, and find the first contact, the second contact. Okay, and that's gonna be your Z limit, right? And the shadow here is this one here, right? That's the shadow. Okay. So anyhow, I'll leave that to you, and not much to see. Problem number 4, you can take a look at the tutorial. Okay, and there's a very similar question for problem number 4. Problem 4. So take a look at tutorial notes, and it's very similar there. Now let's take a look at problem number 5. What kind of possibility difficulty part for problem number 5 here? For problem 5, the first question give you the density and ask you to calculate the mass of this tetrahedron, right? So A here. So the tetrahedron is given by 3 points, okay, and one is basically 0, 0, okay, and the other one is 0, 0, 2, and this is 2, 0, 0, and this is 0, 2, 0. Okay, so you're looking at the tetrahedron. This is a very similar question to what we had in the class. Okay, so apparently what you need to do here is you need to find what is the surface described by this triangle here. And as a matter of fact, if you want to go through the equation derivation procedures, absolutely okay, you'll be able to find it. But a rule of thumb here is this is very simple: x plus y plus z equal to 2. And why is that? If you let x and y equal to 0, you'll get z equal to 2, right? So intersect the z-axis 2. And if you let y and z equal to 0, you intersect the x-axis at 2. So that's how you get basically x plus y plus z equal to 2. Okay. And also you probably will need look at the shadow. If you want to interpret with z first, you'll look at the shadow, which is this triangle here. So the line, this line here, is actually just x plus y equal to 2. It's essentially just let z equal to 0, and that's what you're going to get for this line equation. Okay. So, and I think the integral that is involved is not that difficult. Okay, so you can definitely do the integrals there. Okay, so that's part A. Okay, so not that bad. So let's take a look at part B. Okay, so part B has this density, and the solid is a cylinder bounded by x equal to 1 and 9. So basically this cylinder here is not a traditional cylinder as what we see before, because if this is your x, y, z here, see your bottom of the cylinder, or the circle of the cylinder, is within z and y plane. So you're looking at a cylinder like this and go either way, right? And go either way. However, you do have a bound which is between x equal to 1 and 9. So maybe I'll redraw this cylinder a little bit. Okay, so what you're gonna have is, okay, so if this is x equal to 1 and if this is equal to 9, okay, so you will have two circles. Okay, and this circle center here, and this circle center in here, there. So that's your cylinder here. Okay, that's your cylinder. Okay, and apparently you probably want to use cylindrical coordinates. Okay, now when you use cylindrical coordinates, now this is what you need to do in the class. The formula that we derived for cylindrical coordinates is based on a cylinder whose base is in the xy plane, but now the cylinder, the base is basically in the zy plane, so your cylindrical coordinate in this case here is actually going to be y equal to r cosine theta, okay, z equal to r sine theta, okay, and x equal to x. Okay, so your y-axis is used like your x-axis is in our class notes, and your z-axis is like your y-axis in our class notes. Okay, so make sure you use the cylindrical coordinates properly, okay, and you'll be able to do the integrals there. Okay, now the other thing is when you do the integral, okay, based on this cylindrical coordinates, okay, now what you're gonna experience for the integration over there, you may have an integration of such kind of term here. Okay, yeah. Now when you see this, what you need to do is you need to make use of trigonometry identity. So sine theta square equals to, okay, 1 is 1 minus cosine 2 theta over 2. Okay, so essentially then you can do the integral based on these integrations there. So let me just double check. Yep. Okay, so that's part B. Okay, so part B, make sure you have the cylindrical coordinates selected right. For part C, so for part C, this part here, let's take back here. Part C, you have this as density and the solid as a ball with radius phase centered at the origin. Okay. So apparently, I think that here you would pick spherical coordinates to calculate the mass of the system. Okay, so you would use the spherical coordinates, and spherical coordinates. Don't forget that z equal to rho cosine phi, and x equal to rho sine phi cosine theta, and y is rho sine phi sine theta. Okay, now I don't think you will have a problem finding the limits of for the rho, and phi, and theta. So let's suppose that you're going to integrate in terms of rho first, then phi and theta, right? And also don't forget to substitute the delta with the corresponding spherical coordinates. Okay, so the delta here is x squared plus y squared. So x squared plus y squared, x squared plus y squared turn out to be rho sine phi squared. Okay, then the triple integral is rho sine phi squared and rho square sine phi. Okay, this term is dedicated to the spherical coordinates. Okay. Rho d theta and d phi, or d phi d theta. Okay. Like this. Okay. Now the tricky part here, what I want to see is you have a integral. As you can see here, you're gonna have an integral of a sine cube. So how do you integrate sine cube? Okay. So what I'm gonna see is here basically how to integrate the sine cube. Okay, which you're going to experience here. Now, how to do this? There are a number of ways here. Okay, and the first way, of course, you see, oh, that's too difficult, and then I can take a look at the integration table, and then absolutely okay, you know, you can do that, okay. But what I want to show you is that how do we integrate. You can go ahead and look at the table, and how to integrate this. We can make use of integrating by parts, okay. So the sine theta cube d cube, and you can rewrite as this, okay. And now you're ready and do this integrating by parts. Okay, integrating by parts essentially equal to square, and let the dv equal to sine phi d phi. Okay, so what I can have here, of course, is just d cosine phi, and have a negative here. Okay, and integrable parts will give you this, okay, and this become plus, and cosine phi, and d sine phi square, which is 2 sine phi cosine phi and d phi. Okay, so let's move this down a little bit here. So this term here, this is square cosine phi and plus. Okay. Now this term here, what we can do is we can do this. Okay, we're gonna have cosine phi square, move the 2 here, and sine phi d phi. Okay. Now I think you probably know what to do for this term here. Apparently you can use the substitution rule here, right? Substitution, or you can just simply change this one to this. Okay, so you'll be able to integrate this. So that's how this question goes. Okay, if you see an integration of a sine cube, you can go over these procedures here. Okay, so let's take a look at problem number 6. This question is not that tricky. It has a cylindrical coordinates, so you just have to follow the procedures how to find the integral limits for cylindrical coordinates. So the first step is, as what we do, you draw a arrow lines. Okay, since we're going to determine is to integrate with the z first, draw an arrow line across the shadow. Okay, across the shadow of the solid. Okay, so the first contact is here, second contact is here. Okay, and apparently your z mean is 0 and z max 3 minus y. Okay, and the second step is to draw in reading lines from the origin across the shadow. Okay, so the first contact between the reading line and the shadow is here, second one is here. Okay, so in this case your R mean, okay, is basically your cosine theta, right? It's this circle here. Okay, this circle represents the inner cylinder, and the outer circle, this one here, 2 cosine theta, represent the outer cylinder. So your max is 2 cosine theta. Okay, and your theta angle, okay, is to sweep this line, okay, across this whole shadow. So your theta will be between negative pi over 2 and positive pi over 2. So now you can do the integral as you do in this first stage. Now in this question here, you probably will integrate a term of cosine theta square. Okay, so you will need to make use of this trig identity, which is this, to do the integral. Okay, so you'll go over that by will successfully do the integral. So problem number 7, it's ask you for the volume between 2 spheres. Okay, One of the sphere is this half sphere, and the other sphere is this little sphere inside this half sphere. Okay. So the half sphere is described by rho equal to 2. The little sphere inside that is described by rho equal to cosine phi. Then, according to the procedure for spherical coordinates, so what you do is you start from origin. You draw a reading line out of the origin across the whole region, solid region. Okay, and find the first contact and the second contact between this reading line and the solid region. So the first contact apparently is Z mean equal to rho cosine phi, and the second contact is Z max equal to 2. Right, that's the surface. And the shadow of the region is between here. It's basically this whole circle and here, right? And what you want to do is you draw reading lines across this whole shadow. Okay, the first contact and the second what am I talking about? Well, no, we're talking about spherical coordinates. Okay, so in order to find the next one, which is the phi limit, okay, so what you do is you sweep this line here, and you sweep this line, okay, and okay, so sweep this line across the whole region. Okay, so starting from phi equal to 0 degree, and sweep it across the whole region, right? Okay, so you will see that your phi is between 0 and max, this is 2, and max is pi over 2. Okay, and in the end, theta mean 0, theta max is 2 pi. Okay, so you'll be able to do the integral based on these limits there. Okay, the integration, let me see, the integration is nothing tricky at there, and I think you should be able to do integration. Okay. So let's take a look at problem number 8. So problem number 8 here is also asking you to use spherical coordinates to find the volume between this cone and the sphere. So the cone equation is described by phi equal to 3 pi over 3. The sphere is described by rho equal to 2. Okay, so basically you're gonna go over a similar procedure. Okay, so you draw a reading lines across the whole shadow. First contacts here, second contacts here. So the rho mean is 0, rho max is 2. Then you sweep this reading line, okay, across the whole shadow, across the whole region. So across the reading starts from this cone and ends on the xy plane. So apparently your minimum angle for the phi is going to be pi over 3, and your maximum angle for the phi is going to be pi over 2. Yeah. So sorry, this is minimum, and the max is going to be pi over 2. Okay, and to find the theta angle, so basically you need to sweep this line across the whole shadow, and your theta mean is 0, theta max is 2 pi. Okay, the integration over here is fairly straightforward, and you'll see there's nothing tricky there for this problem 8. You'll be able to do the integration. Problem number 9. Okay, that's problem number 9. Let's move the problem number 9 to here. Okay, so problem number 9 is to basically express the moment of inertia about the z-axis for this solid half hemisphere using cylindrical coordinates and spherical coordinates, and then finally calculate this iz using either cylindrical or spherical coordinates as you wish. Okay, so I don't think you will have any trouble, not much trouble in finding the limits for cylindrical and spherical. The only part is doing the integration of iz. In this iz, what I'm mentioning is in the integration of iz, I think most people would prefer to use spherical coordinates to do the integration, and you will see that you have inevitably gonna have integration of this again. Okay, you have this again. So you can go over using the same procedure that I just introduced for the other question. Okay, and as a matter of fact, in 246, the assignment number 8, you probably will see that one of the I don't remember which question, but one of the forcing function is sine t cubed, and in that question I mentioned that the sine t cubed is equal to this. Okay. So integration of sine, if change the t to phi, so integration of sine phi cubed can be changed to integration of negative quarter sine 3 phi plus 3 quarter sine phi over there. Okay. Now if you want to know why, okay, check the tutorial notes for 246. Okay, in that notes I have given a derivation of how this is equal to this. Okay, so anyway, I think that's possible difficulties that you might experience, and let me know if any other questions. Okay, I'll be happy to answer that. Thank you.